All right, electromagnetism review. Um, so electromagnetism, you should definitely be able to do a loop going through a field and a particle going through a field. And this is a question that has both of those. All right, so we start with, in a coherent paragraph length response, compare the magnitude and direction of the current at times t1, t2, and t3. Include an explanation of why there is or is not a current and the direction of the current if one is present. So we have a conducting loop. At time t1, it's just entering the field. At time t2, it's still entering the field. And at time t3, it's in the field. Okay, so first, let's compare the magnitude. So remember that our voltage in the conducting loop is equal to negative change in flux per unit time. So we need to have a changing flux, okay? And the flux is equal to B dot A, the magnetic field strength times the area, okay? The area in the magnetic field. Now, if I look at time t1, we're entering the field, okay? The field strength isn't changing, but as we enter the field, right, we have just a tiny bit in the field, but as we go in more and more area, we're increasing area, and we're increasing it at a constant rate, okay? So the flux at time t1 and t2 is increasing at a constant rate, which means there is a voltage. So the voltage, or rather the current, since voltage drives the current is equal at time t1 and t2, since we're entering the field. All right, again, we're entering the field, which means our area in the field is changing. Remember, changing is important, and it's the change in flux that causes voltage. Okay, now when we're at time t3, we're completely inside of the field. Okay, the area is now constant. Okay, that means that the change in flux is zero. So for time t3, the EMF is zero, which means the current is going to be zero. So at time t1 and t2, the currents are going to be equal to each other. And at time t3, the current's going to be zero. Okay, that's the magnitude. Now we need to discuss the direction. Okay, so the best way to do this is to do the right-hand rule. Okay, um, so if we look at t1 or t2, right, our velocity is going to the right. Okay, the magnetic field is going into the page. Okay, so your fingers are pointing to the right. Right, remember our right-hand rule, our fingers are pointing to the right. Okay, our palm is going into the page. Okay, so that's going to be X, and that means that our thumb is going to be pointing up. Okay, so that means there's going to be a force on it's a force on positive charges. That means the electrons are going to go down, but don't worry about that right now. That means that there's going to be a upward force on positive charges right here on the right hand side. Okay, on the left hand side there's no force. The top and bottom are going to cancel. Okay, I mean, or they're not going to do anything. Okay, so on the right hand side there's an upward force. Okay, that means the current, and again the current is the direction of positive charges, so that's why the right hand rule works well with the current. So if the current's going to be going that way, we're going to end up with a loop going that way. So the loop is going to be counterclockwise. Okay, at time t2, it's the same thing. We have an upward force here. There's no equivalent downward force on the left, so we get a loop like that. It's counterclockwise, same as t1. Now at time t3, we're also going to have an upward force on this guy. But since the left side is also in the field, there's going to be upward force there. Okay, these guys are going to cancel each other out, which is, another reason why the current's going to be zero at time t3. But we already knew the current zero at time t3 from our are looking at the flux. All right, now let's look at part B. The loop is removed. A proton is traveling to the right in the plane of the page. Enters the region of magnetic field is V equals 3 times 10 to the 5th meters per second. The magnitude of the field is 0.03 T. We can ignore gravity. Calculate the magnitude of the force on the proton as it enters the field. So Fm equals QVB. All right, the B is given 0.03 Tesla. The V is given 3 times 10 to the 5 Tesla. And the Q is given, it says a proton. So I know the Q for a proton is 1.6 times 10 to the negative 19 coulombs. Okay, that's it. Just multiply it. I'm not going to do that. You guys can do that. All right, on the figure below, sketch a possible path of the proton as it travels through the magnetic field. Clearly label a path P1. All right, so for this one, we're going to do the right-hand rule. Okay, so the proton's traveling to the right. I mean, we already did this. Proton's traveling to the right. The B is going into the field, so the F is going to be up. That's the force on a positive charge. This is a proton. That means it's positive. So it's going to loop upwards, and that path is going to be a circular path, not a parabolic path. Okay, a circle is going to look like that. A parabola, if you keep going, is going to look like that. Okay. All right. Next part, a second proton now enters the field at the same point from the same direction, but travels at a greater speed than the first proton. On the figure above, draw the path of the second proton as it travels through the field. Okay. All right. So for this one, we have Fm is causing a circular path. It's equal to Fc. So Fm is QVB, and Fc is equal to mv squared over r, right? Circular motion. Okay, we can cancel out one of those v's. So QB equals mv over r. Okay, now we want to solve for r. So we have r equals mv over qb. All right, so this tells me that if my speed increases, my r is going to increase. A bigger r means a bigger circle. Okay, so when you draw this one, you need to draw a larger circle, right? So, or circle of larger radius. Okay, and that'll be P2. All right, last part. Next, an electric field is applied to the same region as the magnetic field such that there's no net force on the proton. Calculate the magnitude and indicate the direction of the electric field to the coordinate system. Okay, so on the proton, we have a force that's, we have an Fm that's pointing up, so we need an Fe that's pointing down. Okay, and they need to be equal to each other, so there's no net force. So we have Fe equals Fm. Okay, we already know Fm is QVB, and Fe, when we have a magnetic field, we use E equals Fe over Q. That's just the definition of electric field. So cross multiply Fe equals Q times E. All right, divide both sides by Q, and E equals V times B. That's the strength of our electric field. What's the direction of the electric field? Electric field points the direction that a positive charge would go. So I want the positive charge to go down from the electric field. So the electric field is going to be pointing down. All right, so that's a pretty good electromagnetism question. It covers pretty much everything I would want to cover for electromagnetism, so I'm not going to do any more on that. All right, here's a question. All right, this one, clearly it's on the photoelectric effect. I hope you guys can recognize that graph there. So it's about light striking a metal causes electrons to leave, to be ejected. But the AP was thinking, hey, that's a modern physics question, but let's put electrostatics and there's electrons. So um, for part B here, we have an electroscope. Um, the electroscope initially has a negative charge and the leaves are separated. So we start with the leaves separated. Okay, ultraviolet light shines on the sphere, causing the leaves of the electroscope. Ultraviolet light is going to eject electrons. The electrons are leaving. Um, Causes the leaves of the electroscope to move closer together. All right, so what happens is the ultraviolet light causes the electrons to leave, which makes, if the electrons leave, it's going to become less negative or more neutral. So a neutral electroscope is going to see the leaves going closer together. All right, and that's the explanation for this one. So, I mean, they could ask a question where you have some sort of effect making electrons leave something and what would happen to the electroscope. So I just wanted to touch on electroscopes quickly. Okay, so remember, if there's any charge, the leaves are separated. If the leaves go together, that means there's no charge. All right, point charges. I hope this picture looks familiar to you guys. I've definitely given you this question before. On the dot below, draw an arrow that represents the direction of the net electric force on the object with charge plus Q from the other three objects. Okay. Um, so the plus Q, we have three forces acting on it. There's one from this guy that's going to be pushing it away because positives repel. There's one from this guy that's going to be pushing it away that way. Okay, those guys are going to combine and go that way, right? Um, there's also, that's going to be a force going this way. From this guy, it's going to be going this way. So what's bigger, the upright force or the down left force? And the answer is the upright force because these guys are closer. Yeah, those guys are closer. And then, yep, those guys are closer. Okay, so the force on that guy is going to be going to the upright. Don't forget that if you want this distance here is going to be d rad 2, right? All right, for the next part, come on, erase, erase, erase. All right, for the next part, draw the magnitude of the electric field at point P. All right, so electric field goes away from positive and towards negative. So let's do this guy and this guy. It's going to be going away from both of those as that way and that way. That's going to cancel. Okay, so those guys are canceled. All right, now from the other two, we're going to go away from the positive. So from this guy, it's going to go away from that and towards the negative. So it's going to go, we're going to have two going that way. They're going to add up and be like that. So this guy's going to be pointing that way. All right. The next one, calculate the electric potential at point P. Okay. So electric potential is not a vector. We don't have cancellation from our guys here. Okay. But we do have positive and negative. All right. So it's not a vector, so we're just going to add them together. So V equals K Q over R. That's our general formula. So we have, from that one, K 2Q over D. All right. From this one, we have plus KQ over D. Then we add this one, plus K 2Q over D. Then this one, plus K minus 2Q over D. Just add them together. That's it. Make sure you put the negative in for the Q. All right, whatever that comes out to be. Okay, and I just realized in part B, it also says calculate the magnitude of the electric field. So let's do that. Okay, so we're going back to that one. Now, electric field is a vector, so we are going to have canceling because of direction on this one. So let's see. So there's an electric field from this guy and this guy. These two are going to cancel. So we have electric field equals KQ over R squared. Okay. And these guys are not going to cancel. They're going to add together. So we're going to add these guys together. So we have KQ over D squared plus K2Q over D squared. Okay, why don't I put a negative there? Because we're already taking account the negative in terms of the direction of the electric field. Okay, the negative is just the direction for this one. Okay, and the direction is to the bottom left for both of these. Okay, so we add those together, so it's K3Q over D squared. All right, so briefly describe the meaning of electric potential energy. Electric potential energy is energy that's stored in the configuration of charged objects. So what that means is if I have, I don't know, let's say it's just a positive object and I put a proton nearby it, this would be a proton, those guys are going to repel. Just by holding them near each other, this proton has potential energy. And if I let it go, it flies off and we get kinetic energy. So it had potential right there. It's from the configuration of charged objects. Explain qualitatively how electric potential energy can be related to work. As always, work equals change in energy. It's just the work energy theorem. Also explain qualitatively how the electric potential energy of the system would change if the plus Q and the plus 2Q objects on the right side switched. So basically we switched these guys. Okay, before it was plus Q on the top and 2Q on the bottom. Now it's Q on the bottom and 2Q on the top. Okay, support your explanation using appropriate physics principles. All right, so I think the easiest way to think about this, instead of thinking about them as being switching, let's pretend that there's a plus Q on both of them. So we have plus Q, but here we have, on the bottom, we have two Qs. And we're going to take one and just move it up there. Okay. So I want to think about what's happening on the left here. And by the left, I mean relating to the left. Okay. So we have a plus Q charge that's moving from the bottom to the top. Now, when it's on the bottom, the plus Q charge is near the negative Q charge. Obviously, positive charges are attracted, so it kind of likes being in this spot. When we're on the top, it's near the positive charge, which is where it doesn't want to be. So what this is saying is it would take energy to move it from bottom to top, to move the plus Q from there to there. Okay, I need to do work. I need to put in energy to move the plus Q from like this negative area near this guy to this positive area near this guy. So if I'm giving the system energy to do that. That means the system is going to have more energy in this position. And if I let it go, if I let this plus Q charge go, it would be happy to return down here closer to its negative companion. All right. So basically what it's saying is we have more electric potential energy when the bigger positives are near each other, when the plus 2Q is near the plus 2Q. All right, some equipotential lines here. The dots in the figure represent two identical spheres x and y that are fixed in place. Both spheres are charged on y is positive. The lines are isolines of electric potential. The absolute value of the outermost line is 50 volts. 50 volts is this guy right here. Okay, so y is positive. Okay, so the closer we get to positive, the more we're going to be going up. And each it's 10 volts between lines. So this guy's going to be 60 volts, 70, 80 volts. Right? So we have 60 volts and 80 volts. And C would be 100 volts if we keep going. All right, how do the magnitudes and signs of the charge of the spheres compare? So I think it's really obvious when I look at these two spheres that the magnitude on X is smaller. Okay, sphere Y clearly has more charge on it. But the question is X positive or negative? Um, I think the best way to look at that is to draw some electric field lines. So electric field lines are perpendicular to the equipotential lines. Okay, um, so we can kind of see we get shapes like that going there. Okay, and then you go like that. Um, it looks to me like they're both going to have the same charge, and since y is positive, x also is positive. All right. If they were opposite charge, right, we would have this is positive and this is negative. We would have lines that look like the electric field lines would look like that, which means the equipotential lines would look something like that. All right, the spheres at point X and Y have masses in the same ratio as the magnitude of their charges. The isolines of gravitational potential for the spheres have similar shapes to those of the isolines shown. Explain why the two sets of isolines have similar shapes. Basically, they want you to, what they're really looking for is to point out that Fe equals, K Q1 Q2 over R squared, Fg equals G M1 M2 over R squared. Okay, they both relate to distance squared. Um, so if the masses have the same ratio as the charges, the amount that y is like overpowering x is the same, and the distances don't matter because it's r squared for both of them. So they want you to point out that it's a 1 over r squared relationship for both. Okay, based on your answer to part BII, explain one similarity, one difference between the electric and gravitational forces exerted on the proton by the system of two spheres. Well, the spheres are both positive, so one difference is the proton is going to repel from the spheres, whereas gravity always attracts. One similarity would be that the force, again, like I said, the force depends on the distance squared. Um, must not apply to all forces, so that means don't say F equals ma. Okay, part D. At some time after being released from rest at point B, the proton has moved through a potential difference of 20 volts. Okay, determine the change in electric potential energy of the proton spheres when the system has moved through 20 volts potential difference. So it's delta U equals Q delta V, which is also V equals W over Q. Okay, so the change in potential energy is Q, the charge on a proton, 1.6 times 10 to the negative 19 coulombs, times delta V, 20 volts. Okay, as it moved through the 20-volt potential difference, the proton was displaced a distance d by the electric force. Determine a symbolic expression for the total work done on the proton by the electric field in terms of the average magnitude. All right, so remember, work, which is equal to change in energy, is equal to force times distance. Okay, so the force is equal to the work done divided by the distance. Okay, and also force Fe equals Q times E. So QE equals W over D. So E equals W over QD. Oh, did I solve for E? I meant to solve for W. W equals QED. Hey, get it? QED. Cool. All right, two students are discussing how and why the kinetic energy of the proton would change after it's released. Student 1 says if the system is defined as the proton and spheres, the increase in the proton's kinetic energy is due to a change in the system's potential energy as the proton moves through the 20-volt potential difference. Student 2 says if the system is defined as only the proton, the kinetic energy of the proton increases because positive work is done on the proton by the electric field as the proton moves through the 20-volt potential difference. Discuss each student's claims, explaining why each is correct or incorrect. Okay, just checking. It looks like everything they said is correct. If the system is defined as the proton and the spheres, then there's no change in energy of the system. The proton's kinetic energy comes from the system's potential energy, and the change in energy is 0. Okay, student 2 says if the system is only the proton, then there is a change in energy. There's a change in energy of the proton from the system, from the spheres. So work is done on the proton by the electric field. So if we look at just the proton, there's work done on it, increasing its energy. If we look at the proton and the spheres, the proton gains kinetic energy from the system's potential energy. They're both saying the same thing, just different way of saying it. All right, that's it for electrostatics and electromagnetism. I will go over circuits next time. So questions, office hours, or email me, and we'll do circuits coming up.